linear form. Examples of graph is like sine and cosine. We're going to look at methods to solve engineering variables. Example big with that in the collapse the value of m some practice right that we just we'll go through an example. to find I in this equation, and the value in that equation, and determine the and find out your. So what you need to do, a little like heading from that side your graphical area on there. Yeah. Yep, so we got that. Next bit, to fit this straight line, to make the best fit straight line, in the second formula area, if you click on that, and then Y1, you just have to type in Y1. That little symbol means is approximately equal to so we want a quadratic right. If you type next box, that's instead of a best straight line, that graph.
Oh, yeah.
So what is approximately equal to mx1 plus c.
Got it.
Now, what you may notice here is, and I'm going to point it out because someone's going to notice it. Actually, M is on the left-hand side here to 4 significant figures. Intercept is to 5 significant figures. Having said that, what you must remember is this learning outcome is about you doing graphs and interpreting the graphs. So for the assignment, you've got to get your results from the graph, not from that box. It gives you an idea that you've got it right, but when you hand your work in, you've got to show me how you got it from the graph. Not that many, not that many. If you think about, what you should think about with significant figures is how many figures did you have? Remember we talked here about plot on experimental data, measurements that you've made. Okay? These, the maximum you've got here, significant figures, those Y values. To more than 3 significant figures. That's for sure. Okay? And certainly when you do your logarithmic graph plots later, you're not going to get answers on that. It's enough to get 3 significant figures. You're probably going to work to 2. Just bear that. This software will give you a seemingly more accurate answer than you can actually achieve with that. If you look at this straight line, it appears to go right through the points. If you zoom in on those points, they aren't actually right a shape anyway. The idea of doing this graph, if you've got this as current against voltage, find out what current will flow if you apply a bigger voltage or a lesser voltage that you've got. So, looking at the do here, highlight the intercept, equal to 0. 7 point sides of the wood. You really can only take it to 3 significant figures, bearing in mind that we got. So the result constant in our original equation 0.98 from that data. I'm going to able line across there. Choose anywhere. But the two original closest fits. Slope is x2 we need the chunk in slope is engine one you can change that as y2 minus y1. Take away where it started. Divide the right to go from there to there. And x is to 20. Here from my graph, as I got 23.9, oh, I get a slope of 1. A y-intercept constant at 7.98. So I can place that distance back in my original equation, and I straight is equal to 1 plus 7. Just as a check, one of the original data that we had. So I've chosen the data point when I put that back into the equation, 4.2. Closer than now, did the graph. There's a general bit. In there's the constant You used. Algavon. one as linear, like a normal piece of graph, and you can get log-log graph paper. That's what we're going to be using as log-log. Okay? In your assignment, for the merit task, you're being asked to contrast the two different methods that we're using tonight. That is, linearizing the equation to a straight line on normal graph paper or on a normal graph, and then contrasting that with this method of using logarithmic graph paper. When you look at logarithmic graph paper, the numbers don't go like in normal steps like they do on any other piece of graph paper. If we look at, you can also buy logarithmic graph paper with different numbers of cycles on each axis depending on what you want. 2 cycle, 3 cycle, 4 cycle, and you can choose what they are. Tonight we're going to be using 2 cycles on the x-axis and 3 cycles on the y-axis. What you'll note about logarithmic graph paper is each part of the scale does not start at 0, it starts at 1. Remember when we looked at the log function last week? It doesn't exist for values of x where x is equal to or less than 0. So logs don't exist at 0 or below. They start at 1. And that first section, 1 to 10, you notice the gaps aren't the same, but you could use them to represent the numbers from 1 to 10. The next cycle represents numbers from 10 to 100. If you had another cycle, that will represent numbers from 100 to 1,000. It's the index going up by 1 each time. Yeah? Because our function is in the form of a log of a number is equal to a constant times the log of a number, if we plot our original data on log-log graph paper, we should get a straight line. Okay? So if we look at this data, we're going from 1.2 to 11 on the amp scale, on the I. So we need 2 cycles. We need a cycle to cover numbers from 1 to 10 and another cycle to cover the number 11. On the P scale, we've got data that starts at 35 and goes to 2,900. So we need 3 cycles. We need to cover 10 to 100, 100 to 1,000, and 1,000 upwards. So we need 3 cycles on our y-axis. Yep. I'm going to show you what the graph, it's not very easy to see, but that's what your graph when you've finished it will look like. And again, you can find the intercept, and this time, because you're using log graph paper, it will directly read off as the value of r, because this scale is already finding, it knows it's the log of r and it's converting it for you. The scale's doing the conversion. When you want to find the slope here is equal to the change in log of y over x. So you've got a little bit more work here to find what the slope is. I want you to have a go so we can iron out any issues with the drawing on these log graph paper. I've got some graph paper for you. I want you to have a go at that. Okay. Once that is all done, I'll introduce you to the assignment and what you've got to do for that. And then next week we'll have the